Hi, welcome to today's session of organic chemistry. In today's session, we are going to learn about a different class of organic reaction, and it's called nucleophilic substitution reaction. So far in this organic chemistry series, we have talked about free radical substitution reaction in alkane, electrophilic addition reaction in alkenes, and we mentioned a little bit about the electrophilic substitution reaction that happens in benzenes and benzene derivatives. In today's lecture, we'll talk about nucleophilic substitution reaction. First, I'll talk to you about what nucleophilic substitution reactions are, and then I'll give you an idea about what are the components and pieces that are needed to complete a nucleophilic substitution reaction. In other words, what are the substrates, the reactants and products and the conditions that are required in a nucleophilic substitution reaction. And then I'll talk about when does this happen? Or why does this happen? Why is a nucleophilic substitution reaction spontaneous most of the time? We'll talk about in terms of energetics, the energy that's involved in the reaction. And hopefully in the future, we'll talk about how does this happen, the mechanism behind the nucleophilic substitution reaction. Are there nuances to the nucleophilic substitution reaction? Are there different types of nucleophilic substitution reaction? I don't think we'll cover the last part in today's session, but in the future session, we'll definitely go through the detailed mechanism of nucleophilic substitution reactions. Okay, so let's get started. The first part, just look at the name itself. There's nucleophile and there's substitution. So it's pretty clear by the name itself. A reaction where a nucleophile substitutes another nucleophile, that's a nucleophilic substitution reaction. So if you have to describe a nucleophilic substitution reaction to a friend or to your juniors in a sentence using few words, you would say reaction where a nucleophile substitutes another nucleophile, that's a nucleophilic substitution reaction. So let's recap on what nucleophiles were or are. Basically, nucleophiles means nucleus loving, something that loves a positive center, right? Something that would be a negatively charged species, something like a halide ion, hydroxide ion. A negatively charged species would definitely love a positive center, right? Or something that's neutral, but it's rich in electron, something like water. It's not negatively charged, but there are lone pair of electron in this oxygen center, right? So that makes water molecule a nucleophile. Similarly, ammonia. Ammonia is not a charged species, but the lone pair of electron in the nitrogen atom makes ammonia a nucleophile. So nucleophile could be charged or neutral, but in all cases, they are going to love a positive center. They are rich in electron, okay? So there's a little animation I want you to look at here. So this sort of gives you a visual about how nucleophilic substitution reaction work. It's not a holistic picture. It's not it does not incorporate all the nuances, but just to give you a rough idea. So what's happening here is there's a green ball that's approaching. Let's start here. That's the nucleophile, first, the green ball. And the other molecule here on the left, the white and red, that's the substrate, okay? And the substrate has that red nucleophile. This red part is also a nucleophile. So there's one nucleophile, let's get started again. One nucleophile approaching the substrate and substitutes other nucleophile. One nucleophile is coming and making the bond, one nucleophile is leaving. Okay, so a reaction where a nucleophile substitutes another nucleophile, that's a nucleophilic substitution reaction. And this is a generic example here. There's a nucleophile, in this case it's a charged nucleophile, Nu minus, you can see those extra electrons, the rich in electron, right? This is attacking a substrate, which has a electrophilic part, of course, the positive part, that's where the nucleophile is going to go and bond. And there's also the nucleophilic part, which is going to leave. We call this a leaving group, the X part, or the X minus actually. This is the leaving group. This whole thing is a substrate. This is the electrophilic part, and this is the incoming nucleophile, okay? So nucleophile, substrate, the electrophilic part of the substrate, and the leaving group part of the substrate, okay? As a result, the new bond is going to form between the R and the Nu. The X minus is going to go out as a leaving group, okay? So the one on the pink is the nucleophile, the bluish, that's the electrophile, and the greenish part, that's the leaving group, okay? So that's the general background So let's talk about the components. I mean, it's basically what I just talked to you about. Nucleophile, substrate, leaving group, the electrophilic part of the substrate, and then you have the product in which the new bond is formed between the electrophilic part and the nucleophile, and then there's leaving group that's coming out. And you know, all this reaction go through a transition state, right? In all the reaction that you'll encounter in organic chemistry, there is a transition state, which is short-lived, but before the reactants go into product, they have to go through the transition state. So what's happening here is the nucleophile is partially bonded to the electrophilic part, and the leaving group is almost about to come out. So this is like the new bond is almost about to be formed, and the breaking bond is almost about to get broken, right? So that's like the intermediate, not the intermediate, the transition state, and that's the product. So before the reactants get converted into the products, they go through this transition state, okay? And also you can see here, I have two different forms of reaction. The first one, there is a one-step reaction here. We call this one step. The transition step is not counted as a different step, okay? So the nucleophile attacks the substrate, gets converted into product and leaving group. That's a one-step reaction. I call this SN2. I'm not going to talk about the details of the SN2 in this discussion. We'll definitely talk about this in the next discussion. That's a SN2 reaction. And also I have this other nucleophilic substitution reaction on the bottom, in which first the substrate is being converted into a carbocation and leaving group, first step. And in the second step, the carbocation is being attacked by the nucleophile and the product is formed. Same reaction, but happening in two different steps. And that's called SN1 reaction. I'll tell you why it's SN1. Okay, just keep in mind, nucleophilic substitution reaction actually happen in two different pathways, depending on the condition, depending on the substrate. We'll talk about the details of the mechanism in our next session. For now, just remember there are two different pathways that a nucleophilic substitution can take. There's a one-step pathway and there's a two-step pathway. Okay? And this is something I really wanted to talk to you guys for a long time. The whole idea is looking at a reaction from a energetic point of view. Looking at how energy is changing in a chemical reaction and whether the direction of energy movement is going to tell us a little bit about the spontaneity of a reaction. You know, we see a lot of reaction in our daily life, right? Whether it's in our kitchen, whether it's in our electric motor, whether it's in our cell phones, batteries and stuff, there are a lot of reaction. And some of these reactions actually, some of the molecules combine together and do a reaction. There's reaction happening, but there are also a lot of millions and billions of molecules that are coming in contact every day, every second, right? But the reactions are not happening. So what determines whether or not a reaction will happen? And you know, what's the factor? What are the factors behind the spontaneity of a reaction? That's something I want you to, keep in mind. So the graphs, the figures on the side, these are energy profile diagram, which is basically telling you the relative amount of energy, relative energy amount between the reactants and product. In this case, the reactant has higher energy than product. That means the energy is actually going downhill in this reaction, and we call this reaction exothermic reaction in thermodynamics and in chemistry. And most of these nucleophilic substitution reactions are actually going downhill. And in terms of spontaneity, this is a good thing, right? Any reaction that goes downhill in energy, which means if the product of the reaction have a lower energy than the reactant, those reactions are most of the time spontaneous. Okay, I say most of the times. There's also one other factor which is called entropy. Basically the distribution of energy, how is the energy scattered around, that also determines the spontaneity of the reaction. But for now, just think about the energy. Don't think about the spontaneity, entropy. We'll talk about entropy in our future thermodynamics lecture. But for now, just think that energy going downhill is one big factor that makes a reaction spontaneous. Okay? Here, it's a two-step reaction. First, you get to this intermediate, and in the second step, you go downhill. but still if you compare the reactants and the products, the reaction is still going downhill in energy. So both of these reactions are probably spontaneous if there is no significant change in entropy. Okay, so the whole purpose of talking about this energy profile diagram is to see, I have this couple of nucleophilic substitution reaction, and we are going to see whether in this reaction the energy is going downhill or uphill. Okay, and the way we are going to figure out whether the energy is going downhill is by calculating this quantity called delta H, which is enthalpy change. Don't get bogged. This is a pretty simple, it sounds exotic maybe when you hear enthalpy, but it's nothing but energy. Enthalpy is energy. So we are trying to see how the energy is changing when reactant is being converted into a product. Okay, if the delta H for a reaction is negative, that means the product has lower energy than the reactant. Something like this. Delta H is usually calculated by enthalpy of the product minus enthalpy of the reactant. So if delta H is negative, that means product have a lower enthalpy, lower energy. So what we are going to do here is, by looking at the bond energies, enthalpy change can also be calculated by bond energies. Like here, we take the enthalpy of the bonds that are broken minus the enthalpy of the bonds that are being formed. And if we get a negative number here, we know that the energy of the reaction is going downhill. More stable bonds are formed. The reaction is probably spontaneous. Okay, we are going to do that. So let's first see what bonds are broken here. So here we have an alkyl halide. So let's try to name this 1, 2, 3, 4. The longest chain is a butane, and there is a substituent methyl group in the third position. So I would say it's a 3-methyl, 1-bromobutane. Okay, 1, 2, 3, 4. And the bromo is coming up for the first carbon. So I'd say 3-methyl, 1-bromobutane. Okay, and it's being converted into a cyano compound, alkane nitrile, right? So looks like the carbon-bromine bond is broken and a new carbon-carbon bond is formed. Let's try to calculate the enthalpy change for this reaction using the bond energy. Okay, since we don't have the final enthalpy of the product and the initial enthalpy of the reactant, so we can't calculate delta H using the final enthalpy versus initial enthalpy. So there's also other way to calculate the enthalpy change, which is through the bond enthalpies. So I have the bond enthalpies for the relevant bonds in this chemical reaction. So let's use this. Okay, so what are the bonds broken? The carbon-bromine bond is the broken one. So carbon-bromine, so that's 276 minus what's the bond form? So carbon-carbon bond is formed. Carbon-carbon 348. So 276 minus 348. So let's see how much is it. 48 plus what's the difference? 24. 48 and 24 is 58, 68, 72. So negative 72 kilojoule per mole. Okay, that's the enthalpy change for this reaction in terms of by using the bond enthalpies. Okay, so this tells us that the delta H is negative, right? Delta H for this reaction is negative, which means the reaction is actually going downhill. So the reaction is probably spontaneous, and it is spontaneous because there is no significant change in entropy in this reaction, and we don't have to worry about the entropic term, so the reaction is spontaneous. So most of this nucleophilic substitution reaction that you encounter in organic chemistry are pretty spontaneous at room temperature. So you don't really have to use high temperature to undergo these substitution reactions. Okay, so what I want you to do is at this point look at this reaction and calculate the delta H for this reaction using the values that are given here. Okay, see what are the bonds that are broken. There could be more than one bonds. If there are more than one bonds that are broken, you have to add the bonds broken. It's a sigma, right, summation. And also there could be more than one bond that is formed. So in that case, you have to add the enthalpy of the bonds that are formed and get the difference and see if it's negative or positive. If it's a negative, it's a downhill reaction, probably spontaneous. If it's uphill, if the reactant has a lower energy than the product, maybe that step is a little bit harder to undergo. Maybe you have to then provide some extra conditions like high temperature, pressure, catalyst to undergo those reactions. So the whole idea of bringing this topic, the idea of energy and enthalpy, is to is to sort of encourage you guys to understand that the reason chemical reactions happen and the reason they don't happen, a lot of it has to do with change in energy, whether the reaction is going downhill in energy or uphill in energy. And that's a pretty universal fact, not only in chemistry, in physics, or in any other things in nature. You always want to go in the direction of lower energy, right? Lower energy means more stability. You are more balanced. Higher energy means there's a lot of turbulence, right? A lot of disturbance. So just keep that in mind. So from now onwards, whatever reactions you sort of draw a mechanism for in organic chemistry or encountering in organic chemistry, just think about the energy profile diagram and how energy is changing, and try to predict whether or not that reaction is spontaneous or might happen in normal situation. Okay, so let's move on to the next slide now. Okay, so far we learned about what nucleophilic substitution reactions are, right? A reaction where a nucleophile is substituting another nucleophile. What are the components and pieces that are needed or present in a nucleophilic substitution reaction? The idea of an incoming nucleophile, which could be negative or neutral. The idea of the substrate, which is made up of an electrophile part and the leaving group part. The idea of the nucleophile going and forming a bond with the electrophile and the leaving group getting ejected out, right? Those are the components and pieces. We also talked about the two different nuances of the nucleophilic substitution reaction. There are some kinds that happen in one step, right, concerted, and there are also nucleophilic substitution reactions which happen in two steps. In the first step, you break down the substrate into the carbocation and the leaving group, and in the second step, the nucleophile comes and attacks the carbocation and forms the new product, right? The SN1 and SN2 reactions. In our next session, we'll talk about what kind of substrates would undergo SN1 reaction, what kind of substrates and under what condition would they undergo a SN2 reaction. That's for the next lecture. We also talk about what drives a nucleophilic substitution reaction and what drives the chemical reactions in general, right? We talked about it from an energetics point of view. We talked about the downhill energy going reaction and uphill energy going reactions, right? And most of the times, if entropy is not changing that much, reactions that go downhill are probably spontaneous, are more likely to be spontaneous. And we also calculated the delta H for one nucleophilic substitution reaction using the bond enthalpies, because we didn't have a ready-made final enthalpy and the initial enthalpy of the reactants and products. That's why we used the bond enthalpy and calculated the delta H. We found one of the reactions was spontaneous because the delta H was negative. And I asked you guys to sort of calculate the delta H for the other reaction. I gave you the bond enthalpies. I want you to go back and do that. And like I mentioned before, I'm going to talk about how do nucleophilic substitution reactions happen. We are going to talk about the mechanism. We are going to talk about the nuances. Okay, we are going to talk about the SN1 and SN2, the one-step and two-step reactions of nucleophiles. And for this, you need a lot of arrow pushing diagram practice. So I want you to practice the arrow pushing diagram. Where does the arrow start from? Where does it end? Where is the head of the arrow? Where is the tail of the arrow? Where do we draw regular curved arrows? Where do we draw the fishhook arrows that we talked about in the free radicals reactions? Okay, just like, yeah, just try to develop more interest, try to research a little bit more yourselves, practice more problems, take more examples. There are a lot of examples in Google and YouTube that you can sort of go over. So yeah, if you do that, I feel like your foundation would be ready for learning organic chemistry and organic chemistry reactions. Okay, so yeah, thank you for listening. I'll see you guys next time. Thank you.